looking at page 26, just a review of inverse trig functions before we get into differentiation and anti-differentiation. So you might remember the notation and the names of these things from pre-calc, but then again you might not. So here we are. Okay, so just very quickly I'm going to take you through some of the more important characteristics and details. So we start off with the cosine function. We know the amplitude of the cosine function is equal to 1. So I'm not going to use the whole graph. I'm just going to use one box to represent one unit. Cosine graph starts off at its maximum point, and a quarter of the way through the period it hits the midline. Then halfway through the period it hits the minimum, then 3/4 of the way back to the midline, and then back to the maximum. So we want to go out to 2 pi here. So I'll do this in red. A quarter of the way we get to the midline, then the minimum, then back to the midline, and then back to the max. And this is one period of the cosine wave. What we want to do is graph the arc cosine. Alright, so that would be the inverse or arc cosine of x on the interval of -1 to 1. Alright, so every coordinate when you graph an inverse gets swapped. So 0, 1 gets plotted as 1, 0. So I'll make this 1, 0. This point here would be pi over 2 comma 0. So we're going to plot 0 comma pi over 2. Next up we have pi comma -1. So we'll plot -1 comma pi. After that we would have 3 pi over 2 comma 0, at which point we would plot 0 comma 3 pi over 2. The problem with that is if I do that, it's going to put me up here and I will fail the vertical line test and not have a function. So don't want to do that. In fact, if I go beyond the point that I last plotted at -1 pi, it's going to create that looping back upon itself effect and cause this to not be a function. All right, and we want it to be a function. So we'd have to stop there, and we could not go any further than the 1, 0 in the downward direction. So what we do is we restrict this by saying that the arc cosine function can only exist between 0 and pi. Well, arc cosine is y. All right, so this is the expression that we're using to define y. Y is between 0 and pi. All right, and that's because x over here was, it was between 0 and 2 pi, but we could only go so far before it would loop back upon itself. So we need the original function to pass the horizontal line test in order for the inverse function to pass the vertical line test. Right? So once the original function fails the horizontal line test, we stop including those x values. Those x values, when converted over to an inverse, correspond to y values. All right. Now we wouldn't just define this by saying that the x values have to be between -1 and 1, because that doesn't help, right? Because this point up here has an x value between -1 and 1, so does this and this and this, but it's still not a function. All right, so we would have to actually restrict the y's here rather than the x's. All right, so we're actually looking at the range rather than the domain. All right, little issue with the font there, but hopefully you get the idea. 0 less than or equal to arc secant of x, and that's because we're living in the world of cosine, so what's true for cosine would be true for its reciprocal function, right? And that's secant. But it can't exist at, x can't exist at pi over 2. All right. Oh, apologies. Y can't exist. Ay, ay, ay. So I'll actually just write arc secant of x cannot be equal to pi over 2. All right. The reason why we wouldn't say x is because x isn't an angle when we're dealing with inverses. X is a ratio. All right. So if we actually get a little bit more specific here, you can see that this is an angle. The y, I mean, that's the cosine ratio, adjacent over hypotenuse. So now x here is the ratio, and y is the angle. All right. Now looking at the sine function, this is going to go from negative pi to pi. So normally the sine function starts off at 0, 0. On a 2 pi period, it'll hit the maximum point at the quarter way to the 2 pi, which is pi over 2. Then it would hit the midline at the halfway point, and then continue on, right? But we want to go from negative pi to pi, right? So we'll follow the trend in the opposite direction over to negative pi, and you see that that's going to complete one full wave of the sine function, all right? So now we want to graph this. If I start off with the 0, 0, which is the most convenient point, that's going to be easy to plot. Then we have pi over 2 comma 1, which would plot to 1 comma pi over 2. Then if we plot, this would be pi comma 0, that would plot to 0 comma pi. We run into the same issue we had before, where it would loop back upon itself and fail the vertical line test. So we don't want to do that. All right, so we're going to exclude any value that exists beyond the pi over 2. But that requires us to go in the opposite direction to complete one full cycle. All right, so if I go over to this point here, I'd have negative pi over 2, negative 1. So that would be negative 1, negative pi over 2. But again, if we continue on, it would fail the vertical line test, so we disregard any point beyond that. So our y values here would exist between negative pi over 2 and pi over 2. Since cosecant goes hand in hand with sine, we can assume the same restrictions, right? But we could also assume the same typo. So this should be but arc cosecant of x cannot be equal to 0. Yeah. So, and you could already see the same typo for the last piece. Right, but anyway, so we're going to graph the tangent of x on negative pi to pi. So people are generally very familiar with sines and cosines, less so when it comes to the tangent function. So if you have to go to your calculator for this, that's fine. But the unit circle is also a really good resource when it comes to coming up with trig function graphs. Right? And that is because we know tangent is sine divided by cosine. We can just kind of work our way around the unit circle and figure out the values as we go. All right? So tangent is 0. tangent is 0. That's the brightest thing I've said all day. Tangent of 0 is 0. And that's because sine of 0 is 0, cosine of 0 is equal to 1. All right, we're only going out to pi, so I'm going to choose some convenient values. Like, for example, how about pi? All right, you can get tangent of pi, which is sine of pi over cosine of pi. Sine of pi is 0, cosine of pi is -1. All right, so that's going to give me another 0. All right, but now we want to think about values along the way. All right, so for example, I mean, in this case, it's broken up into quarter unit increments, so let's make use of that. So at pi over 2, sine of pi over 2 is 1, cosine of pi over 2 is 0. All right, so that's going to be undefined. That's also going to happen at negative pi over 2. And really, any multiple of pi over 2 that puts the angle on the y-axis. All right. So we know we have asymptotes there. Well, how about pi over 4? Tangent of pi over 4 is equal to 1. It's all a question of where you want to put the 1. Just to be consistent, I'll put it here. And that's because sine of pi over 4 is radical 2 over 2. Cosine of pi over 4 is radical 2 over 2. Anything divided by itself is 1. All right? Negative pi over 4, same reference angle, but in the fourth quadrant, only cosine and its reciprocal are positive, so we would expect a -1 as a result there. All right? And I know to place it here because half of a half is a quarter, so it makes sense to put pi over 4 at this location. All right. So since we know it's going to be asymptotic and go through 0, it's going to look something like this. Now, I could continue on, and if you know anything about the tangent function, you know that it's periodic, just like every other trig function, but it has the same pattern. What's going to end up happening is it's going to fail the horizontal line test for the original function. That means that it's going to fail the vertical line test for the inverse function. All right. Now, the question did say to graph it, so you know, we do have to graph it. But that being said, I'm only going to take note. I'm only going to really care about the curve in the middle or in between those two asymptotes. All right, so we're looking at something like this, but I'm going to put a nice little highlight over that middle one. Make it look all nice like. All right. Now 0, 0 is going to plot nicely. Pi over 4 comma 1 is going to become 1 comma pi over 4. So here's 1. Pi over 2 is established to be 3 boxes, so pi over 4 will be 1.5 boxes. So I'm just going to put it right here. All right. We know that there is a vertical asymptote at pi over 2 in my ordinary function graph, so there's going to be a horizontal asymptote at pi over 2 for my inverse function graph. Same idea for the negative pi over 2. All right. -1 comma negative, negative pi over 4 comma -1 is going to become a -1 comma negative pi over 4. So that's going to put a point right here. All right. Now, you may look at it and say, well, I don't know if I have enough points to really get an idea what this graph is going to look like. So that's up to you. Generally, we just follow the trend of the original function and use that to help us come up with the graph of the inverse. You use a graphing calculator if you want, but you could also just grab another point. You know, something between pi over 4 and pi over 2 would be pi over 3, for example. So you could do that. You know, pi over 3, if you plug that in for sine, you're going to get radical 3 over 2. Plug it in for cosine, you're going to get 1/2. So it's a radical 3. All right. So you really just looking at the square root of 3, which is about 1.7-ish. All right. So 1.73 in that neighborhood. 1.73, 1.74, but we'll use 1.75 just because, why not? It's cleaner, and we're estimating anyway. All right. So now in terms of plotting the pi over 3, well, that's the same as 60 degrees. All right, 60 degrees is 2/3 of the way between 0 and 90. So 1.75 and 60 degrees would look something like that. So now I'm kind of at the point where I'm confident in saying that it's going to look along those lines. It's going to have some kind of point of inflection. It's going to send it back the other way. I mean, we could grab another point if we want, but this is, we're pretty confident in saying that this is what it's going to look like. Now, if you want, like I said, we've got all this stuff in here, but we can clear it out and put in inverse tangent of x, zoom trig, zoom 7, and just have a look. Right? We could also go to Desmos. All right, if you go into, well, let me put y equals first, y equals. Go into functions. Under trig, you see all the different options. One of them is inverse tangent. Nothing showed up. Yeah, well, look at the scale here. Hit the home button, that's default zoom, and you see we have a nice looking graph there. All right, so a lot of different options, not the least of which is comfort with the unit circle, which allows you to be able to visualize this stuff in your head. All right, that's going to play a pretty important role as we go forward. Between this course and really any other course that follows, if you don't have a good sense of the unit circle, there is a price to be paid. All right. So we now know that the arctangent function is only going to exist between negative pi over 2 and pi over 2. And we make the fix here. Honestly, I think I just got bit by the copy-paste monster here, because really this one's kind of a disaster. Because I really wouldn't say this. I mean, I guess I could, arctangent, but arctangent can't be positive or negative pi over 2. But as you probably noticed, an easier way of saying that would be just to, it's got to be greater than, it's got to be less than. That would have done the trick, and I wouldn't need this. All right, so I don't know. I just don't know. Anyway, oh, and there's a good-looking typo right below that. Geez, this one's all over the place. Negative, negative. I mean, there's a place for that mathematically, but this isn't it. So anyway, so why the difference in domain, or in this case, range, for arc cotangent, where we didn't have really any kind of change in range for sine and cosecant, secant and cosine, but this pair of cofunctions definitely has one, and that has to do with the placement of the asymptotes. So let's take a look at the tangent function. All right, it's going to be a mess, but I'm going to put it in anyway. So I'm going to put it in as a ratio, sine over cosine. And I'll do it all in Desmos in a sec as well. A little dead air here, sorry. Like a Yankee game. All right, so let me turn one of them off. Hit enter on the equal sign to turn the graph off. I'm going to do zoom 7. That's what my tangent function looks like. All right. If I were to plot the vertical asymptotes, you'd see them at each of these open tick marks. All right. It's kind of tricky to plot verticals in the TI calculator, so I'll show you that in Desmos. All right, so let me turn the other one on. You say, oh, okay, well, it just seems like it's a reflection of the previous one. So still, why the change in range? Now let me graph them both simultaneously. All right, so here is, or the unbolded one. I mean, like, here is the tangent one. Yeah, well, here it is. Why? Because that's where it is. Yeah, this is the tangent, and that's going to be unbolded. All right. So hopefully you can tell, but not only is there a reflection allowing it to, instead of being an increasing function, to be a decreasing function, but there's also a shift. All right, and if you go by the x-intercepts, it's kind of hard to keep track of, but if you go by the x-intercepts, you could see that this one has an x-intercept of 0, but this one appears to have an x-intercept where the other graph's vertical asymptotes, or vertical asymptote is. All right, so one graph's x-intercepts becomes the other graph's asymptotes. All right, so that explains, in a sense, it explains that there is a difference in range, but it doesn't necessarily get at y. All right, what does get at the y is the fact that the denominators are different, yeah, but they lead to different asymptotes. So the denominators of cosine tell us that we'll have asymptotes whenever cosine is equal to 0. So it's anywhere on the y-axis. Pi over 2, 3 pi over 2, negative counterparts, any other, coterminal angles. With the cotangent, the sine function is the denominator, telling us that this will have a vertical asymptote whenever the sine function is equal to 0. That's anywhere the unit circle is on the x-axis. All right, so that's multiples of 0 and pi and 2 pi and all that. All right, so that should kind of give you a sense, but there is a little bit of a difference there. All right, now just so, one, I could show you how it's done, and two, it actually kind of looks nice. I'll bring it up in the in Desmos. So inverse tangent. Now let's get inverse cotangent. One of the many things I like about Desmos, and I prefer it to the TI calculators, not the least of which is because it's free. TI calculators, the price hasn't changed really over the years, even though the technology, the price hasn't changed, and neither has the technology. So it hasn't gotten any better, and they still charge the same amount. All right, so that's bad news, but also this gives you a nice refined product. Also, it's not just going to limit you to the sine, cosine, tangent, and their inverses. It gives you all the reciprocal and inverse functions as well. All right, so let me get my inverse cotangent, and you can see that there's a nice shift here, and because of that, it would make sense that the range would be different. So let me plot the range, or at least horizontal lines representing the range of the tangent function, and I'll do the same thing for the cotangent. So y equals negative pi over 2 and positive pi over 2. Little duplicate action here. Duplicate, hit that little double page icon. Change the minus to a plus. And so you can see that it kind of captures the tangent function. All right. Whereas, and I'll just duplicate one of them. This one is going to go up to pi. I'll use the x-axis to be the other border. So this is going from 0 to pi, capturing the entire cotangent function. All right. So a lot of good stuff going on here. Although I think I kind of lost part of my, because I made one of them. That was weird. Okay, anyway, but you have a nice looking graph there. Right, and color coded, and you could change the thickness. Long press on it, you change the thickness, change the color, change the style. A lot of good stuff with Desmos that you don't necessarily get with the TIs. All right. So that's a little bit of a recap on how you, or I was going to say how you graph inverse functions, but also some of the characteristics of the graphs of inverse functions.